Okay, so we're going to finish off electronegativity. No, I guess we did finish that off. What did we do last time? We did talk about polarity of bonds, right? Yeah. Okay, well, we'll just review a lot of that. And then we'll review Lewis structures. I know we did it in lab on Tuesday. But we'll do a couple more just to make sure via CPR as well. And then we'll get to the kind of the goal is to figure out polarity of a molecule. So, just a reminder, or review, I guess, bond order. This is whether you have a single, double, triple bond. It sounds redundant, but we have to have bond order because we're going to eventually talk about fractional bond orders, so bond order is a thing. As the bond order goes up, the bond gets stronger. The bond energy goes up as well. Think of the bond energy as the amount of energy you need to put into it to break that bond. Conversely, when you make a bond, the molecule's energy goes down. So it must release energy when you make a bond. When you make a bond, energy is released. So breaking a bond, you have to add energy. Anyway, we'll get back to that because that's going to be a big thing we'll talk about in future chem classes. The bond length. The longer it is, the weaker it is. The shorter it is, the stronger it is. So these correlate very, very, very well. Okay. We also calculated average valence electron energy. This is just a slightly more complicated ionization energy. But instead of focusing on just the easiest to remove electron, we looked at all of the valence electrons and did an average of them. So it's similar. It has the same trend as ionization energies. As you go left to right, they increase. As you go top to bottom, they decreases. And we start seeing some trends. If you look at more on the periodic table, for instance, metals have generally less than 1.06 average valence electron energy. Non-metals greater than 1.26. You don't need to know those numbers. Just get comfortable with the idea that you can predict lots of things with these values. So this is leading us to electronegativity. So electronegativity is something completely different. It is defined as the ability of an atom to attract electrons at a bond. So two atoms sharing electrons in a covalent bond. Sometimes that sharing is imbalanced. It's not even. One atom might attract those electrons a little bit more often than the other. And remember, we're thinking quantum mechanics. We don't know exactly where the electrons are going to be, but we can say that the electrons tend to hang around one atom more than the other. If one atom is more electronegative than the other. Yeah.
I wanted to clarify. So when it's partially negative or partially positive, it still can mean that the electrons, do they only hang around the partial negative area, or do they sometimes hang around the partial positive?
They do hang around. So they're still being shared. So that both atoms still feel the sharing the electrons. But in terms of what is the probability of finding the electron here in the middle versus closer to this atom versus closer to that atom, the probability of finding it on one atom is going to be higher than the other atom now, if there are differences in electronegativity. Does that make sense?
So with hydrogen and lithium, it was the partial negative charge that they were hanging around, which was the red color, correct? And then the other one you showed us, which was like hydrogen fluorine or something like that. It was the partial positive that they were hanging around. So it can be either.
Oh, so the partial negative denotes the where the electrons are most likely to be found.
So it is partial negative.
Yes, the electrons are negatively charged.
So they like.
So if they're going to hang around, if they're going to hang around one side of the bond more than the other, they're going to make that side of the bond more negative.
Oh, okay, that makes sense.
That makes sense?
That makes sense.
Okay. So yeah, normally the bond is neutral, completely evenly balanced.
Like that green one.
Yes, but sometimes they hang around one side more than the other and create a dipole. Yeah. Okay. So electronegativity, these are properties of an atom, just to make sure these are not measured. Like electronegativity is not something you can measure directly. It's an artificial construct scientists created. We have various ways to calculate this kind of concept, depending on what theories you're interested in, figuring out. So one of them is average valence electron energy. That's why we studied AVEE, because it's a good way to lead into where does this electronegativity number come from. But depending on which way you calculate electronegativity, you get all these different tables. So the tables in the worksheets, the welcome table in the worksheets is not the standard electronegativity. The Pauling scale is the standard one, the one that everybody uses. But again, there's plenty of them. They're used for different reasons. So sometimes you use bond energies to calculate them, which we haven't talked about yet, or haven't used at least. They're also relative. So there's no units on them. So it makes no sense to talk about fluorine having an electronegativity of 4, and that's it. It's only useful when you're comparing it to another one. That's what it means to be relative. So fluorine 4 versus carbon 2.5, when you compare the two numbers, oh, fluorine's more electronegative, then it has meaning. That's what it means to be relative, okay? Otherwise, it's an absolute number, which is the number itself has meaning. So, yeah.
How do you spell that? Pauling, you said?
Pauling, Pauling.
Oh,
Named after Linus Pauling, the scientist.
And you said that they have no units, but they're relative only in comparison to another atom?
To another value. So one electronegativity value by itself doesn't mean much, but when you compare two of them, then they have meaning. Okay. That's just all it means to be relative. So I think we did these. This is just, yeah, I think we did these. I'm going to skip this. And again, we have one way to calculate an electronegativity using average valence electron energy. You multiply any of those AVEEs by 1.8, and you get approximately a good value for an electronegativity. All right. So trends, we have covered this. I'm going to skip that real quick. Here is the Pauling scale in periodic table form. In Pauling's version, fluorine is exactly 4, carbon's 2.5, hydrogen's 2.1, things like that. Those are the ones I memorized. You don't have to memorize any of these values. What you should though know is the trends and approximately where carbon or hydrogen falls. Hydrogen is somewhere between boron and carbon. Okay. Yes.
The numbers, do they at all say anything about the relativity of hydrogen and boron? Since hydrogen is 2.1 and boron's 2.0, they're almost identical in electronegativity. So does that say they're anything alike? Or is it just?
No. All we can say is that if you made a bond between boron and hydrogen, that they would share electrons pretty evenly.
Okay.
That's it. That's pretty much it.
Okay.
Yeah.
So no answer is acceptable here, but on the periodic table, iron, cobalt, and nickel are all in the AVE category, and they
Yes.
all have like pretty similar electronegativities. And what is the reason?
What is the rationale?
Or is there a connection, I should say?
So I'm trying to remember. Generally, the groups were formed because of similar properties, and so the Roman numeral with the letter after it, that's the old group numbering system. The new one is very boring. It's 1 through 18. But the old one, the old one was developed because of similar grouping, similar properties. So something, I don't know exactly how they grouped it, but somehow iron, copper, cobalt, nickel, and the rest of those underneath have similar enough properties that they put them in the same group.
Okay.
I don't remember anything more than that, honestly.
That's fine.
Yeah.
Okay.
Yeah. Okay. So, I think we've started covering this last time. So polar, non-polar. Yeah, okay. We talked about the color. So let's go through this kind of quickly. Yeah, we did this. We did this. I'm in the wrong slide deck. No, I'm not right. This is 15. Okay, we're good. Okay. Okay. So I think we did this as well. So we looked at HF to HI, and I guess just to point out, the difference between red and blue is very distinct here, which tells you that this is a very polar bond. But as you get to, and the red side is pretty much to one side of the molecule. So you can really see that this side of the molecule is slightly negative, that side is slightly positive, very polar. When you get to iodine, though, or iodine, that partial negative charge is kind of in the middle again. And you can't really say, oh, one side of the molecule is negative, one side's positive. It's not as clear. And if you look at the difference in electronegativity, there's a very little difference in electronegativity between hydrogen and iodine. So this is really kind of a nonpolar bond. Even though there's a small difference, this is approaching what we'd call nonpolar. Whereas this one here is very, very polar. Okay. So this leads to something new here. And I'm going to put a caveat on this. And it's already asterisk. There's already a caveat right there. Technically, to be nonpolar, the difference in electronegativity should be 0. And there's going to be plenty where the difference in electronegativity is 0, especially if you match two fluorines, two nitrogens, two of any of the same atoms. The difference between those two is 0. There's other bonds like carbon and sulfur. Carbon is 2.5, sulfur is 2.5. They have 0 difference in electronegativity too. But there's plenty of kind of gray area bonds. So CH. The CH bond, and if you look these up, carbon is 2.5, hydrogen is 2.1. The difference in electronegativity between these two is 0.4. That's about as big as the previous HI bond that we saw. And you can see, you saw that like the electrostatic potential thing, you couldn't really see a positive or negative side of the molecule. And that's the kind of the same for any kind of CH bond. Even though there is a small difference in electronegativity, as chemists, we consider this a nonpolar bond. So this thing is kind of lying a little bit. Technically, the cutoff is somewhere around here. And there's no clear cutoff. That's why we don't really mark it, because it depends. There's a few other factors that come into play. But around 0.4, that's kind of where you can start to say, it's about nonpolar here. Okay? Yeah.
The polarity of each of these, are they molecules when they're together? Like CH or?
Well, so this is not a full molecule. This is just a single bond.
Just a single bond.
Yeah.
Their polarity is what makes them attractive or less attractive to other atoms.
Yeah.
Other bonds to make a molecule or a substance. So their polarity is. Let's put it this way. The effect of polarity is, there's a lot going on. So one effect, and here I'll just give you one. This is water. Water is very polar, and because it's so polar, it dissolves things like salts very easily, like ionic compounds, very, very easily. And it's because it's polar. If it was not polar, so a solvent that is nonpolar can't dissolve ionic compounds. So that's one effect polarity will let you do. It'll let you predict, hey, this will dissolve, this won't. Polarity also, and this is going to be relevant in organic chemistry if you ever take it, but polarity, so if you have a molecule and you've got a very polar bond in it, that's a very popular target for other molecules to react with. So like, if I compare like this is pentane, and it's just all carbon-hydrogen bonds. Is pentane a type of gas? Well-
So this one's a liquid, barely a liquid. Butane is a gas.
Okay.
One extra carbon. Butane is 4 carbons. Pentane is 1 extra carbon. So this is barely a liquid. But this is very nonpolar. I couldn't dissolve any salt in this. This is like gasoline almost. What was I getting to? So this is very unreactive. I mean, yes, you can burn it very easily, but when it comes to reacting with other reagents in organic chemistry, you know, if we tried to react it with chlorine or something, it just doesn't do anything. But if I throw in a scenario like this, where suddenly I have a very polar bond in it, those polar bonds become targets because of this is going to have a partial negative charge, that's going to have a partial positive charge, and that polarity, that dipole moment, is a place where other chemicals can come in and say, oh, there's extra electrons there, I'm going to attack
So
there.
like a magnet.
It's like a magnet
Around
almost. Yeah,
it.
it's a, you know, most of the time a reaction you could boil it down to this thing wants electrons. So if it sees an area where there's a rich concentration of electrons, that's where it's going to go.
Okay.
So this is going way in the future, but
Oh.
but polarity is a big deal. Understanding polarity is very important in chemistry. So technically, again, the cutoff is somewhere around here, 0.4 is nonpolar, and then above that is polar. So that's why it says 0 by technicality. So ignore that. Just say 0.4 about. Now, when you get to above 2, suddenly it switches to ionic. So, I mean, think about why that would be. If I have lithium with fluorine, and I try to make a covalent bond between them. Yeah, your question?
Sorry. So instead of delta En equals 0, we should write 0.4.
I would say, yeah, as long as it's less than 0.4. Less than or equal to 0.4. It's a very gray area cutoff, so depends on the molecule, depends on the bond. We're not going to get into like the nitty-gritty in this class, but I'm not going to trap you in any answers. Let's put it that way. So, again, why do covalent bonds form? Covalent bonds form because most things want to have an octet. They want to have 8 electrons around them. They'll share electrons if they have to. Lithium and fluorine. Well, so fluorine is this. 7 electrons in the valence shell. Lithium is, sorry, let me draw this better. This, it's got 1 electron in the valence shell. Okay, you guys know metal and a non-metal make ionic bonds. But let's say that this tried to make a covalent bond. If I shared these two, I would get something similar to what normally looks like, you know, what you would get for any other covalent bond. I'd get 8 electrons around the fluorine. The lithium would get a duet, 2 electrons, kind of like hydrogen does. But, you know, is that feasible? Well, if we look up the electronegativity for lithium and fluorine, lithium's electronegativity is 1.0, fluorine's is 4.0, and the difference in electronegativity here is a whole whopping 3.0. That's a huge difference in electronegativity. So remember what electronegativity means. It's the ability of one atom, in this case fluorine, which is higher, to attract shared electrons. So if I tried to make a covalent bond between lithium and fluorine, this fluorine is attracting these shared electrons so much that it's just ripping the electrons completely away from the lithium. And instead of making a shared bond, the fluorine will just take the electron completely and leave you with the anion. And so that's an ionic bond. So that's why anything greater than 2.0 difference in electronegativity tends to make an ionic bond instead of a shared bond. Okay? So we're kind of now talking about bonding as a spectrum, not just a black and white thing. Like, oh, it's ionic or covalent. We're moving away from that black and white thinking, although we can still categorize them that way. But it's more of a spectrum. There's going to be, hey, it's more ionic, more covalent. So, yeah. So non-polar covalent bonds, those are easy to spot. Polar covalent bonds are pretty easy to spot. There are some ambiguous ones, but like I said, I've modified that little table to show you that if the difference is about 0.4, I would call it non-polar. And then when the difference in electronegativity is big enough, it becomes ionic. So here's that spectrum I was talking about. We can also start calling, we can still say this is a covalent bond or this is a polar covalent bond. But something that is a polar covalent bond, you can say also it's got some ionic character to it. It's not fully ionic, but it's got some ionic characteristics to it. And the same goes in the other direction. If I'm going towards a very non-polar covalent bond, I would say the covalent character is increasing. We're not going to do it, but we can start assigning percentages even. Like, hey, it's 70% covalent, 30% ionic. That's what it means to be on this kind of a spectrum. In 222, I keep talking about 222, we're going to throw another wrench into this and introduce the metallic bond, which is the third kind of bonding. And you'll have this triangle where you can plot the kind of bonding on either it's fully ionic, fully covalent, fully metallic, or somewhere in the middle. And then there's going to be semi-metals thrown in. So it's a spectrum, okay? We're not going to complicate things too much. We're going to simplify for this class. We're just going to just identify something as non-polar covalent, polar covalent, or ionic at this point, okay? I just don't want to make you guys too dependent on those definitions. All right, so what do you guys think the CO bond is? Which one? CO bond. Oh, we got a little bit of variation here. So most people think D, and it is D in this case. So honestly, the one way to do this, there's really only one way, is if you want to know exactly what kind of bond it is, you have to look it up in the table of electronegativities. You'll get one in the final. You don't have to memorize any of this. But C is 2.5, O is 3.5. The difference is 1. So don't make it negative, just whatever the difference is, make it positive. And 1 is squarely right in the middle of that chart. That's polar covalent. 0.4 to 2 is polar covalent. Yes?
How do you know if it's ionic or polar ionic?
Ionic is the only kind of bonding there is. There's no such thing as polar ionic. So that's a fake answer. All right. Good question though. Yeah.
To be clear, oh no, you can change the slide. But the reason that boron, silicon, germanium, and those are semi-metals is because of the electronegativity with the non-metals is just almost 3.
So it's the same reason. So remember that the electronegativity follows AVE. It follows ionization energies. These are like right in the middle. They're not super low. They're not super high. They're kind of between metals and non-metals. So that's why they are treated as a semi-metal.
Okay.
And they have those properties. Yeah.
What is the number, the electronegativity number for a non-polar covalent bond? Or maybe you already said.
Oh, between 0 and 0.4.
Okay.
So just hardly anything. Okay. So which one is really quickly most polar? polonium here is sometimes colored metallic, sometimes colored semi-metallic. The issue is it's so rare, and they haven't been able to synthesize a large enough sample to really probe its properties to see whether it's truly metallic or truly semi-metallic. So sometimes you'll see it either one. It's kind of interesting. We do know it kills people. That's what the KGB used to kill some defectors. Or not the KGB, the FSB. That's what they are now.
Some Twitter.
They killed some guy in London. Poked him with a little needle. No, this is like spy
Joys of
stuff.
chemistry.
You guys heard about this? They had a little needle on an umbrella.
Yeah.
And there was polonium on the needle. I think there was. Or am I thinking of the T? Maybe it's the T. They did it. I don't know. They did the needle and they did the T too. But
I heard this on a podcast.
yeah. And then the guy just got slowly sicker and sicker and sicker and sicker and just died. Just took him forever. It was a horrible death.
Chemistry.
All right. So.
Get away with murder.
Yeah, it's pretty bad. CO is going to be your most polar. Okay, so just you can calculate all of them, but kind of remember that the difference, if there's a large distance between them, they're going to have a large difference in electronegativity. Yeah.
Yeah, why isn't it C because the difference between N and H is bigger?
So, so remember that even though hydrogen is up here, in terms of electronegativity, it's right about here. So 3.1 minus 3.0 minus 2.1 is 0.9,
Yeah.
whereas 3.5 minus 2.5 is 1. That's higher.
Oh, I need, yeah.
Okay, yeah, overlooked it. Okay. So, yeah, just look for the biggest separation first. That's kind of a big clue, and then check those numbers. But N and O are right next to each other. They're going to be smaller, things like that. I think we saw these or something like it, but we don't normally care about the values of what these charges are. All right, so a partial charge we do know is less than 1. If it was a full +1 charge, it would be ionic at that point, which they're not. So these are partial charges, but you can kind of see if we actually calculate or measure these charges, we can kind of see the strength of the polar bond with this. So HBRs, the partial positive on H is actually a +0.09 charge, very small. And the on the bromine, it's the opposite, minus 0.09. For HF, it's almost a third, 0.29. And then for the fluorine, it's minus 0.29. It's a bigger charge because HF is more polar. The difference in electronegativity between H and F is a bigger difference. And that's actually one of the most polar bonds that there is. And even the most polar bond is still about a third of the charge, not even half. Yeah.
How do we find the charge?
You're not going to have to calculate what these are. Don't worry about it. But one thing that's clear is the charges have to balance out, because these are neutral molecules, HBr, HF, they're 0 charge overall. So the two charges on each of the hydrogen and the halogen have to cancel out. They have to balance out.
Is that for them to be non-polar?
Well, no, for it to be a neutral molecule.
Oh,
It is a polar bond though, because so it is definitely polar, but the overall it's neutral. Yeah.
So that I mean, obviously there's some correlation to electronegativity, but 4 minus 2 is like still 2. But so we just don't know how to calculate these numbers yet, right?
What do you mean 4 minus 2? Where do
Like
you
the
get this from?
electronegativity of fluorine is 2,
Yeah.
is 4, and hydrogen is like 2.1.
Right.
So it'd still be like 1.9.
Oh, I see what you mean.
We just don't know how to calculate these yet, right?
I think so. It's not just. I actually don't know how they calculate these. I mean, we'll actually do these calculations next week in the computer lab. That we're gonna do.
Cool.
But it's all computer based. I'm sure there's equations we can use, which is not necessary for us to learn. That's all. Okay, so some of the partial charges is 0. We know that. So we've talked about the dipole moment. We talked about this arrow, I believe. The partial positive, partial negative symbols are sometimes adequate to show this dipole moment, to show that this bond is polar. But sometimes we want a different way to show it, and this is one way to do it. This actually represents something slightly different. So these are actually just showing the actual charges. But this represents is a dipole moment, which is a measurement of that dipole moment. So you're measuring the strength of that. Yeah, I guess you're just measuring the strength of that. How do I describe this? It's weird to describe fundamental things. The strength of that separation of charges, basically. So if this was like a north and south pole, that makes a magnetic dipole. I would call that moment, the magnetic moment, the strength of the magnetic field. I guess this would be like a strength of the electric field that this is generating. But anyway, all this is doing is showing exactly the same thing these charges are doing. It's pointing towards the partial negative. The tail is on the partial positive side. And I think I've mentioned this if you have taken any vector calculus or linear algebra. That's a vector, and vectors have two meanings. The length is kind of the size. It's kind of the measure of the strength. And it's got the direction has meaning too. So the direction is telling you which way the negative is, okay? But if you don't understand vectors, don't worry about it. We're going to use them in a very simple way.
Can you go back for one?
Oh, yeah.
Thank you.
So, there it is. It's a numerical indication of the magnitude of the polarity of a bond or molecule. It's a fancy way of saying not much, honestly. But that mu symbol, that's the symbol we'd use as a variable in an equation. So if you ever see that, that's what it is. We're not going to worry about that too much. Yeah?
Isn't that the same symbol as micro?
It is. So micro is a unit, or it's a prefix, I should say. But that, you would see it as a variable. So,
so instead of like x, like
yeah,
mx
you see
plus
mu.
b would
Yeah.
be, it would be m.
So mu equals some number, and then the unit is there, d. A new unit for you guys. This is a weird one. I don't use this ever. Nobody uses this, but you can measure the dipole moment, and the unit for that is a debye. It's a very specialized unit, okay? So we're going to see this next week in the lab as well. What can we do with it? Well, we can use this to kind of gauge the strength of the dipole moment, to gauge how strong the polar bond is. So the larger this number, the more polar it's going to be. The smaller that number, the less polar it's going to be. All right, so a non-polar bond will have 0 debye for its dipole moment. There'd be no dipole moment. The length of this arrow corresponds to the size of this number. Okay, so that's kind of what the arrow is good for. It's a visual description of the dipole moment. Okay. So, we'll do a few of these really quickly before we move on. Because again, the goal is not to worry too much about the individual bonds. We want to be able to measure the dipole moment or figure out if a whole molecule is polar.
Is what we're doing here going to be, is there something on the exam?
Yes, this is all going to be in the exam.
Like set up this way, where it's going to, it'll ask, hey, do the partial charges and the arrow and.
Yeah. I mean, you're not going to have to come up with the numbers.
Oh, good.
But you'll have to like, hey, this atom has the partial negative, this one has the partial positive, this is the way I draw the arrow, things like that. So, OH, if I have this bond, I would label the partial charges, well, look to see which is the most electronegative atom. And I don't have a table in front of me, but I know that oxygen is more electronegative because it's closest to fluorine. So the most electronegative element is going to get the partial negative. And then the other one is going to be the partial positive. Again, we don't care about the actual charges, we just know that this one's negative, this one's positive. As far as a polarity arrow, this dipole moment vector, we always draw the arrow towards the negative side. And the tail is going to start at the positive side, and we put a little plus at the tail. That's just convention. is this bond nonpolar, covalent, polar, covalent, or ionic? Well, now we kind of need the numbers. And I'm going to just tell you what they are. So oxygen is 3.5. Hydrogen is 2.1. That difference is what, 1.4? I do this in my head. Yeah, 1.4. Making sure. That's pretty big. That is a very polar covalent bond. This is actually one of the most important polar covalent bonds. It's what makes water what it does, what it is. Sugars, alcohols, anything that has an OH in it is very important in biology, in biochemistry. So if I compare that with SH, and I know I wrote it backwards, but it's okay. Same thing. So sulfur is more electronegative than hydrogen is. Let's just write down the numbers. It's sulfur is 2.5, not 3, 2.5. Hydrogen is 2.1. This is one of those where the difference in electronegativity is pretty small. 0.4. That's kind of right on the border of what we said was kind of nonpolar. So I'm going to say it's nonpolar, or very, very weakly polar, whichever you want to say, but it's nonpolar covalent. It does have a slight dipole still. There is a difference in electronegativity, but when I draw this arrow, so let's do the partial negative, that one's partial positive. This arrow is going to be tiny, or at least for this one, because the difference in electronegativity is so small. I mean, I'm calling it nonpolar, so there really shouldn't be much of anything. So if I were to draw an arrow, it'd be very, very short, something like that. Okay? It's very relative, like whatever you draw is fine. But if I compare that to CI, and if I look these up, this one I'm going by memory, but I'm pretty sure carbon is 2.5 and iodine is 2.5 also. Thank you. Those are exactly the same. This is very definitely nonpolar because the difference in electronegativity is 0. You cannot draw a dipole moment. There is no dipole moment at all, and there is no partial negative nor partial positive. They're the same charge on both sides. These electrons are being shared completely equally. Okay. So that's the kind of thought process you need to go through when you see every single bond in a molecule. Right now we're just looking at one bond at a time. But we're going to move on to whole molecules. I'm going to stop it there. I feel like we're going to end early today, but we'll see.
Do we not need to draw the charges and arrows because they're the same?
So there is none. Yeah. So there's no charges because they're the same electronegativity. There's no side that's positive. There's no side that's negative. Yeah. And since there's none of that, there's no arrow. There's no dipole moment.
So that green in
yeah, it's gonna look greenish everywhere.
green, just a
Or
sphere.
Well, it may have some red in it, but the red will be kind of in the middle. It won't be on one side or the other.
Right.
And when it comes to what is the dipole moment, this one I know for a fact is going to be 0. I don't know what these are, but they'll be greater than 0. This one will be really big. This one will be small.
And the nu was the dipole moment symbol again?
This is mu, mu.
Mu,
Yeah,
and it's
that's the micro symbol. Yes.
and it's the dipole moment.
Dipole moment. Yes.
Okay, mu.
Just to be clear, what are the units of divide? Is that an energy unit?
You gotta put me on the spot. I gotta look it up. I don't know.
That's fine.
I'm sure there's some kind of energy in there, and it's derived from energy probably, but it's probably not exactly energy. Sorry. So, which of these have a dipole moment? I guess there's only one you could pick. So, oof, okay, not everybody answered the same. So the answer here is C, and you kind of just have to look at the electronegativities again. If they have the same electronegativity, it's going to be nonpolar, and there will be zero dipole moment. So FF, same. C and S, same. FE and Ni, they're the same. But C and Cl are different. And so that will make a polar bond. Not very strongly polar, but polar. And so it will have a dipole moment. It will have some positive dipole moment. Okay. So, if HCl's dipole moment was 1.11 divide, what might the dipole moment of HI be? And you don't have to know the number, but which one makes sense? Got a big group of answers here. The actual answer is going to be, if my thing works, is D. So HCl has a certain polarity to it. We can compare the difference in electronegativity between H and Cl. Cl is not the highest electronegativity, but it's close to fluorine, so it's pretty high. Hydrogen is kind of low, so it's going to have a pretty big difference in electronegativity. It will make a pretty polar bond. I is further away from fluorine. It's less electronegative than Cl is. So HI is going to be less the difference is going to be smaller. The difference in electronegativity is going to be smaller. And so the polarity is going to be weaker, a lot weaker. So the dipole moment should be less than this. And that's why 0.45 is the answer here. It's not going to be 0. If you had a table in front of you, you can look up H and I. I is 2.5, H is 2.1. So that difference is what we would call nonpolar, formally, technically. Not technically. Practically, that's the word I'm looking for. Nonpolar practically, but there's still a difference. And so there's going to be a weak dipole moment, and that's why it's a small number like this. There's no such thing as, you're not going to have any negatives. That just doesn't really work this way. So it's going to be 0 if it's completely nonpolar, like the same electronegativities completely. It's going to be this if it was HF. So if the dipole moment was stronger than HCl, then it would be a higher number. But this is a weaker one. Okay. So now that we've kind of covered just plain bonds, let's switch to molecules. And this is what we covered in the lab. We went over how to go from a formula to a Lewis structure, and then from a Lewis structure to a shape. And it's pretty important when we start doing polarity of molecules to get to the shape part. So let's kind of practice that really quickly. So you cannot find the polarity of the molecule without going through these first two steps. You have to. So if I gave you NH3 and I asked you what is the polarity, unless you've memorized it, you have to first draw a Lewis structure, then you find the shape, and only then can you find the polarity. And this is tedious, but it's critical that you go through these steps. So let's. I'm going to skip this slide. So I went over a slightly different method for doing Lewis structures than what this slide shows. I think my method goes from here to 3 pretty good well, and then it differs when it's 4 or 5. So ignore that. The one I talked about in lab works a little bit better, I think. At least I'm more familiar with it. So let's practice doing some Lewis structures in a second, but let me we didn't go over this too much in the lab. There's plenty of exceptions to the octet rule. So we've already seen hydrogen. Hydrogen is happy with 2 electrons. And that's because shell 1 only has s orbitals in it, so that can only fit 2 electrons, that's it. But helium is just the same way. Not a big deal. We don't really make compounds with helium, so it's not a huge, we're not going to see that very often. But here's some other ones that we didn't talk about. Boron and beryllium. So boron's number 5, beryllium's number 4. They do some weird stuff. They actually are fairly happy without having a full octet. So they make very stable compounds, like with having 6 electrons around them. So I think you'll see some examples in your homework, but you don't have to know anything fancy. You just need to realize that if you ever see a boron compound that looks like this, BF3, that this is fine. Even though it looks weird, this is a stable boron compound. So boron here has 2, 4, 6 electrons next to it. Doesn't have an octet, but that's okay. Beryllium is actually the same way. You can make these weird BeF2 compounds. And this beryllium only has 4 electrons around it. This does it that way. Anyway, so these two kind of break the octet rule by having fewer. However, carbon, nitrogen, oxygen, fluorine, a lot of the nonmetals have to follow the octet rule. But then, when you get beyond, or when you get to period 3 or below, or higher, I should say lower on the periodic table, you can actually have more than 8 electrons. And so, if there are going to be cases where there's no way to add your electrons to your Lewis structure unless you put them on the central atom and then you're breaking the octet rule, that's okay. The third shell is where the d orbitals begin, right? So there's no such thing as a 2d orbital, but there is a 3d orbital. We don't fill it until we get to the transition metals, but even in row 3, the 3 d orbitals exist. They're just empty. So if you have to put extra electrons, they can fit into the d orbitals, and that's why you can break the octet rule that way. Yeah?
I don't understand why boron and beryllium don't need octets.
It's not something we can explain exactly. Well, I can explain a little bit. So the idea here is, what are the core charges of boron? +3. So one way to think about it is that there is not a strong attraction. Boron does not have a super strong attraction to electrons. It's not like a metal where metals just want to give up their electrons and make cations, right? Metals like to lose electrons. Boron is a semi-metal, but it doesn't have a very strong attraction to electrons anyway, and so it doesn't need all 8 electrons to be, like the noble gas, to be stable. It doesn't need as many, because it's got a lower core charge than the rest of the nonmetals. That's probably the best explanation I can give you. As far as anything more concrete than that, I can't really tell you. It's just the way it happens, the energies work out where boron is stable like that. Okay. So you just have to memorize boron and beryllium as they make weird compounds. In fact, there's a whole, when I went to grad school in UCLA, there was a group there, and all they did was boron chemistry, because boron was just weird. Did stuff that most people don't study, and so their group was dedicated to making odd boron compounds. I don't know how practical it is, but I'm sure they've been around for a long time. Okay. Sometimes pure research doesn't make much sense until you suddenly a discovery is made. You're like, oh, that's what this is all for. So anyway, yeah, this is just double checking. So let's practice a couple structures really quickly, just to make sure that this is all clear. And I'm going to start with nitrate, even though I know some people have done that already. So my technique for doing Lewis structures again is first count total valence electrons. So nitrogen, group 5. So that's 5 electrons from nitrogen. The oxygen is group 6. So each oxygen contributes 6 valence electrons. There's 3 oxygens. So I'm going to multiply by 3. And then finally, if there's a charge, any negatives add electrons. Any positive charges remove electrons. So this -1 electron, or sorry, this -1 charge adds 1 electron to your total number of electrons that this compound comes with. So 24 total electrons. That's step 1. Step 2, we're going to do a skeletal structure, meaning we're going to put one atom in the center. Usually it's the first one, unless it's hydrogen. But more specifically, find the least electronegative atom usually goes in the center. Sometimes it's kind of written out the way that it should connect. So pay attention to how the formula is written. Sometimes there's a clue in it. But in this case, nitrogen's in the center. We're going to put the oxygens all around it. It doesn't matter exactly where you put them, as long as they're around it. And I'm going to connect the central atom to the outer atoms with one bond each. And every bond you draw is a pair of electrons. So I'm going to subtract each of these electrons from my total. 2, 4, 6. Now I've got 18 left. So all of these electrons need to be drawn in on this structure. That's the point of keeping track. So step 3, you do the octet rule for the outer atoms. So this oxygen has 2 electrons next to it. It needs 6 more to have a total of 8 electrons. So I've drawn in 6 more. I'm going to subtract those 6. 12 left. I'm going to keep going around. So this needs 6. Plus the 2 there makes 8. And then this needs 6 more. Plus the 2 next to the bond makes 8. So I'm out of electrons. Now I'm going to look at the central atom, satisfy the octet rule for the central atom. 2, 4, 6 electrons. This needs 2 more. But the problem is I don't have any more. I'm out. All electrons need to be drawn in. They're all drawn in, but I can't draw extras because I don't have any extras. So this is where I share. I'm going to take a lone pair that I previously just drew in, and instead of putting it just on the oxygen, so this one for instance, I'm going to share it between the oxygen and the nitrogen. So when I do that, I get that. So that is a very good version. There's 8 electrons around the nitrogen. The last thing, just to make it perfect, make it clean, this is an anion. So we need to show the charge, and you show a charge on the Lewis structure by putting a square bracket around it, and then the charge just goes on the bracket. So that's nitrate. And that's the basic steps. Question, yeah?
So we've only been really given molecules with even electron numbers.
Yes.
That's through convenience or something that just happens in nature?
It generally just happens in nature, but there are examples where there's odd numbers. And if you've ever heard of radicals, free radicals, that's what happens when you have odd numbers of electrons. So they are very, very, very reactive species that will attack anything. And you can draw them with Lewis structures, but they don't really fit the mold because they don't do octets, which explains why they're so reactive. But we're not going to do them because it's a little advanced. We'll save that for organic chemistry when you take organic.
Okay. and you said those are called radicals?
Yeah, free radicals. Or radicals in general, yeah. The peroxide. Yeah, so it's kind of weird. So the whole ozone depletion, the reason that happens is because of the free radical process. So it was CFCs in aerosols was, I don't know, ozone depletion was like so 80s, but it's still a big deal. there are CFCs, chlorofluorocarbons in aerosol propellants. So any spray can, hairspray use CFCs, and air conditioning use CFCs too. And those chemicals, which are basically chlorofluorocarbons, so something like that, or maybe more complicated even, but chlorine and fluorine in them. They would, in the upper atmosphere, get hit by sunlight, and the sunlight would break bonds and create radicals. So these atoms that have an unpaired electron in them. And then those would go and find ozone, break apart the ozone to make plain old oxygen, and then it would leave a free radical, which would then attack the next ozone. So it was a catalytic process. Like a little bit of CFCs would destroy tons of ozone. It wasn't one for one, yeah. So that was a big deal. And ozone blocks UV rays, so without ozone we'd get sunburn, and it was all bad. All right. Yeah, question?
Oh, it can wait for a little bit. It's about the final, not the
Okay.
section we're on.
Okay. So we'll do a few examples in a little bit because I want to get to the rest of it. But once you have a Lewis structure, now we're going to find. Oh, question. Yeah, sorry.
I guess I was supposed to final, but are we gonna have this on like the final? Okay.
Will you be given this?
This
graph?
table?
This table.
No.
Oh, okay, that's what, so we need to like memorize it.
So yes and no. You only need to know the top part. You don't need to know trigonal, bipyramidal, and octahedral, and the subshapes. You don't need to know this, but you need to know these. So you need to know how to get from here to here without this turn. So how do we use it? The more you use it, I think I would use the computer software, like the PhET, P-H-E-T, just to kind of get a good visual on these shapes. They make sense to you. But to use this thing, I would look at my Lewis structure and I'd say, how many groups of electrons, how many electron domains are on that central atom? You look at the central atom only, don't care about these. So there is a double bond here. Those electrons don't come apart. They stay together. There's a group here and there's a group here. 3 electron domains. And so this fits into trigonal planar. That would be the electron geometry or electron domain geometry. That is the shape that the electrons force it into. And then you count, okay, of those 3 electron domains, how many of them are used for bonding? Well, all 3 are used for bonding. So the molecular geometry is also trigonal planar. If, for instance, and I'm just going to erase this temporarily, if, for instance, there was a lone pair on here instead, like that, that's still 3, 1, 2, 3 electron domains. Still be trigonal planar electron geometry, but there's only 2 bonding. There's only 2 bonding domains, and so we would call this bent. And that's kind of what you're seeing, right? It's bent. If you look at just the atom part, the bent molecule. So that's where these names come from. And that's why there's a difference between electron geometry and molecular geometry. You have to find the electron geometry first, then you can do the molecular geometry. Because the molecular geometry depends on the electron geometry. Okay, but it's not this. So let me redraw it so it's not confusing. Okay. The other thing you need to know from this is bond angles, although you don't need it for what we're going to do. You need to know that in general, trigonal planar is 120-degree angles, linear is 180, half a circle, and tetrahedral 109 or 109.5, same thing, or close enough. That's the bond angle for tetrahedral bond angles. The other thing you should know how to do is draw them 3-dimensionally.
Oh, don't move on. I was trying to get the bottom there.
Well, this is actually right from the lab itself. So
From Tuesday?
in your lab intro, in your lab manual, like this whole thing is from the lab manual.
For next Tuesday or the one
For
we did?
the one we just did.
Okay.
Yeah.
Okay.
you also need to know how to draw it, and again, don't worry about the last two. Please don't put dots in the middle, put whatever the element is. But, you know, carbon here, and then if you're doing tetrahedral, the solid wedge comes towards you, the dashed wedge comes away. That's how we do perspective in chemistry without being an artist. So, that's probably the only hard one to draw. Okay. So that one's drawn correctly. It's trigonal planar. I mean, mine's rotated, but it's the same shape. So, let's do another one. Let's do xenon F2. Why not? So this is neutral. That's going to be easier. Xenon is a group 8. 8 valence electrons. Phosphorus. Fluorine is group 7, so 7 valence electrons, and there's 2 of them. So 14 and 8 is 22. And we'll do our skeletal structure next. Xenon in the middle, fluorine on either side. Again, where you put the fluorines exactly doesn't matter. Lewis structure, only thing that matters are the connections and the number of electrons, okay? You can do the shape afterwards. So, 2, 4 electrons I've already drawn in. I've got 18 left. I'll do the outer electrons first, or sorry, outer atoms first. So 2, 4, 6 plus the 2 here makes 8. So I'll remove 6 here. Need 8 on this side, so 6 more plus the 2 here makes 8. So I've got 6 left, and now I'm going to do the octet rule for the central atom. Well, the xenon has 2, 4, and I need 4 more. 1, 2, 3, 4. So I've satisfied the octet rule for everything, but I have 2 electrons left. I have to draw them in. They come with the molecule, so I have to draw them. The Lewis structure shows the position of every valence electron. So where are they going to go? Well, they cannot go on the fluorine, because fluorine is row 2, it's shell 2, it only has s and p orbitals, that's it. Fluorine has no d orbitals that you can add extra electrons to. But xenon does. So xenon has empty, let's see, 6d orbitals that we haven't used yet. No, 5d, excuse me, 5d. The 5d orbitals are empty. So we'll put them in the 5d orbitals. So I'm going to move this over just to make it look clearer. Is with the originals. And then these 2 I'm going to put in right there. So this is xenon difluoride. As far as the shape goes, go back a little bit so we can see the chart. I have 1, 2, 3, 4, 5 groups of electrons. 1, 2, 3, 4, 5 around this xenon. So the electron geometry is trigonal bipyramidal. But it's not going to look like that. Like the molecular geometry doesn't look like that, because like that's what trigonal bipyramidal looks like. There's like 5 things attached. But so it doesn't look like that because there's only 2 bonding pairs. Only out of the 5, only 2 of them were bonds. And if we look at this table, 2 of them are bonds. It's linear. So the molecular geometry is linear. And basically that's kind of why I drew it like this. This is how it looks. There's a fluorine, a xenon, and a fluorine all in a row. It's linear.
You're not going to be giving us a trigonal bipyramidal.
Yeah, so you won't get that in the final, but that's basically how you do these. Yep.
So why wouldn't that be been in? Oh, because the 3 go on the outside and the fluorines are on the top.
So this is a good question. Trigonal bipyramidal is more complicated because the axial positions and the equatorial positions are slightly different. it's better to put the lone pair electrons in the equatorial positions because they can be 120 degrees away from each other rather than 90 degrees away from each other. So the lone pairs want to be in that position. That's why they're on, these are on the opposite sides, yeah.
So, the 2 bonds on the side and then the 6 electrons around it. The 6 electrons are not bonds, right?
Yeah, they're lone pairs, yeah. So they're just kind of loose, they're, yeah, unused electrons, but they're part of the shell. Maybe shell's not the right word. They're part of the molecule. Okay. Should we do another one?
So just to be clear,
Yeah.
things like chlorine, argon, aluminum, silicon, those in the 3rd period, they could fill their 3D modules, right?
Yes.
Okay.
Yes. Aluminum less likely because aluminum's a metal, and aluminum will probably rarely will make covalent bonds.
Okay,
Yeah.
fair enough.
I guess we can do. Let's do OCN because that's a good one to do next. Where the camera can see that one here. So OCN, this is one of those where it's kind of laid out or written out the way it should be drawn out. Usually that's a clue. So I'm going to put the carbon in the middle, the N on one side, and the O on the other. So I've done the skeletal structure first. Let's do the electron count. There's 6 for the oxygen, 4 for the carbon, 5 for the nitrogen, and since it's a minus charge, an extra electron. So 16. So I've already drawn in 4 electrons, 2, 4, subtract those. And then we're going to do the octet rule for the outer atoms. So the oxygen and the nitrogen. So 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. And if I get to the central atom, I want to do the octet rule. I have 0 electrons left. So I have to share. I have to take lone pairs I've already drawn in and move them to the bond part. So the question is, do I take, so I need 4 electrons, extra electrons on this carbon. So do I move 2 lone pairs from the nitrogen? Do I move 2 lone pairs from the oxygen, or do I do 1 each? So let's do 1 each first. So if I make this pair, move it here, and I'll move this pair, move it here. That is a Lewis structure. That works. There's 8 electrons on the carbon, 2, 4, 6, 8. There's still 8 around the nitrogen, 2, 4, 6, 8. There's still 8 around the oxygen, 2, 4, 6, 8. So this one works. Kind of. And we'll come back to that in a second. So, this is where we're going to get into something called resonance structures. So sometimes there's more than one way to draw the Lewis structure that fits the rules. So everything has an octet, everything's fine. So, and that was the case here. I could have done 2 lone pairs from the oxygen, or I could have done 2 lone pairs from the nitrogen. So I could have drawn it a couple different ways. I could have drawn it like this, where I left the oxygen alone and just moved 2 lone pairs from the nitrogen. Or I could have done it like this, where I left the nitrogen alone and moved 2 lone pairs from the oxygen. So every one of these is a resonance structure of each other. These are a set of resonance structures because they are acquired by only moving electrons. We're not moving atoms around. All right. If you move the carbon here and the nitrogen here, that's not a resonance structure. That's a completely different molecule. So the atom placements have to stay the same. The only thing that can change is where the electrons are. So how do we know which is correct?
Sorry, can you just go back up this?
Yeah, okay. We got plenty of time, so don't worry.
Would you just give me a brush up on we talked about how it's like 1/2 the bond number of bonds and then
Yes,
number of
formal
bonds.
charge. We're going to do that next. Yeah.
Oh, okay, never mind.
Yeah,
never
we'll do it
mind.
next. So, there you go. So, there are going to be cases where these are equal, like they're all likely, and there's going to be cases where one is better than the others. To understand what is better, which one is correct, which one's not correct, we have to do something called formal charges. And we have to calculate a formal charge for every single atom. So 9 different formal charges here. These are not charges like charges on an ion. They're not that. They are, again, like a tool. They're something chemists make up in order to understand what's happening with electrons. Kind of like core charge. It's not a real thing, but it's a good way to understand what's happening. So that's kind of what formal charge is. And yeah, so I guess I'm not a fan of that definition, but I've read it, and a lot of books say that formal charge is the charge an atom would have if all bonding electrons were shared equally. Kind of. It'll make more sense when you get to organic, let's put it that way. But right now, let's use this as a tool to find which one of these resonance structures is the correct structure. And I really should have put the bracket around all of them. They're all negative. But anyway. So the equation for calculating formal charge, and I like the bottom one better, but they're the same, is the number of valence electrons that were originally on that atom. So just look at the periodic table. Subtract the number of non-bonding electrons. So like these oxygens, these are non-bonding electrons here. Lone pairs. And then half of the bonding electrons to that atom. So if I go through and, oh, I did this wrong. There should be 1 lone pair, not 2. Sorry. Let me redraw that. My mistake. So let's go through and calculate the formal charge on every single atom in these 3 resonance structures. So for that oxygen comes with 6 valence electrons. It's group 6. These have 2 non-bonding pairs of electrons. So 4 non-bonding electrons, 4 electrons in lone pairs. And then there are 4 electrons in bonds. So half of that, that's equal to 0. So that oxygen has a 0 formal charge.
I don't understand where the half.
It's part of the equation. Half of all bonding electrons. So there is 2. So on this oxygen, what's bonded is 2 4 electrons.
Sure.
And I'm just taking half of that number. So next to carbon, we're going to do 4 valence electrons, because it's group 4. There are 0 lone pair electrons, and half the bonding electrons. There's 2, 4, 6, 8 bonding electrons are on that carbon. So 0. And then finally the nitrogen. 5 is the valence electrons. That's group 5. Minus 4 lone pair electrons. Minus half the number of non-bonding, or half the number of bonding electrons, excuse me. So 5 minus 4 is 1, minus another 2 is a negative 1. So finally we get to our first non-zero formal charge. And you're going to show that with a circle around the charge. So negative, with a little circle around it on the nitrogen. We put circles because without the circle, that line looks like a bond. It's confusing. So put a circle around it so it's not confusing. Same for the positive. And it's also a way to distinguish a regular charge, like that one, from a formal charge. Formal charges are not regular charge. They're not the same. So we have to go through each one of these. And if I do it here, I get 0 here, 0 here. If I do the oxygen over here, let's do that. I'll do that one real quick. 6 minus 6 lone pair electrons minus half the number of bonding electrons. There's 2 of them. That's a minus 1. A little arrow there. There we go. And I'm going to put a little minus formal charge on this oxygen. And then finally, this one down here. This one's a little bit crazier. Let's do the nitrogen first. 5 valence electrons minus 6 lone pair electrons minus half the number of bonding electrons. That's a -2. That's pretty big. So there's a -2 formal charge in the nitrogen. The carbon ends up being a 0. And I'll just take a shortcut here. The oxygen ends up being a +1. So we've done all of the formal charges on every atom. And you will get better the more you do this. So what do those tell us? Well, first of all, the sum of the formal charges for a neutral atom will be 0. But if it's an ion, the formal charges will add up to the charge of the ion. So that's one way to make sure you've done it right. So this is a -1 ion, so an anion. So if I add up all the formal charges, they should add up to -1. They do. -1. Here's a +1 and a -2 that adds up to -1. It's again a way to double check you did it correctly. Now, last thing.
Sorry, just real quick. We want the formal charge that we want that would be considered the correct resonance structure is the one with the larger or the smaller. I missed that part.
So yeah, I haven't talked about it yet. It was in the lab. Let's do it now.
Okay.
So when you've drawn in all your formal charges, number one, you want structures that have 0 formal charges, or at least the fewest formal charges. None of these have no formal charges. They all have some. This one has 2 formal charges. These have 1. So this one's probably out. You also want the smallest formal charges. So any 2s, bad. 1's better than 2s. So this one's definitely out. This one's no good. These formal charges are way too big. There's too many of them compared to the other ones. Do you have a question?
I'm just like, so we want the smallest formal charge, or?
So if I had a structure, if a resonance structure up here that was 0, 0, 0 everywhere, that's the best one. But if I have, like, all of them have some formal charge on it. This one has 1, a -1 here. This one has a -1 here. This one has a plus and a -2. So we want to avoid resonance structures that have many formal charges and large formal charges, if we can. Now, these two look identical, but the last rule is any negative formal charges should be on the more electronegative element. So between nitrogen having a -1 formal charge and oxygen having a -1 formal charge, that one's better. Because oxygen is more electronegative than nitrogen is. So in terms of which one is the correct Lewis structure, that one is it. How would we know that this is correct? Like, what can we do to verify it? Well, if this is the correct Lewis structure, we could try to measure bond lengths. What do we know about triple bonds versus single bonds? Triple bonds are a lot shorter. And they're a lot stronger too. So we should see properties of this molecule where this bond is pretty long or easier to break if this is the correct resonance structure. If this was the correct resonance structure, then this would be the strong bond, this would be easy to break, but it's not.
So what I wrote is more electronegative atom with identical formal charges between the resonance structures is the correct one. So that is the most.
So you want negative formal charges to be on the more electronegative atom.
Oh.
And if it was the opposite, if you had a positive formal charge, you want that to be on the least electronegative element.
Okay.
If you have a choice for that. Yeah.
Okay.
So why isn't it the first one then, because that one has like, I don't know if formal charges for carbon and nitrogen are different in the second one and the first
So I didn't show the calculations for these two, but for this one it ends up being 0. This one ends up being 0 too. This one ends up being 0. That nitrogen ends up being 0 when you calculate it. So I kind of skipped it, but when you calculate everything, you'll get zeros somewhere. You'll get -1 somewhere. You get plus.
So then, what is the reason? Like the first one is the same thing. It's just the oxygen is like the first one also has 1, -1, and 2.
Yeah. So in terms of the numbers of formal charges, they're similar. So now, okay, well these are similar in terms of quantities of formal charges. Like that has a -1 and that has a -1. Well, then we have to look at where is that negative formal charge, what atom is it on. It's better to have a negative formal charge on a more electronegative atom. Alright, so think of a negative, so what does a negative charge ultimately overall mean? It means extra electron. That's in my mind, that's what a negative charge means. Electrons are negative. So if you're going to have an extra electron somewhere, it's most likely going to be on an element that likes electrons, an electron that is very electronegative. Yeah, question?
So if I drew either the top one or the bottom one, that would be marked as wrong on the exam?
Oh, well, so you probably will have to draw all three as part of the question. Like, what are the resonance structures? Well, yeah, I guess if you try drawing this one or this one as a final answer for what's the Lewis structure, you'd probably not get full credit. Yeah. These are valid Lewis structures, but the correct Lewis structure is the middle one. This is a more extreme case. So this is carbon dioxide, but you know, you could also draw it this way, where all of the sharing of electrons comes from one oxygen only. But if you calculate formal charges on this is 0, that's 0, that's 0. And if you calculate the formal charge on this one, you get a -1 here, a 0 here, and a +1 there. And that should, you know, you should have alarm bells in your head. If this is 0 everywhere, and that's got +1 and a -1, that's no good. We want the one that is 0 formal charges everywhere. And that's the correct structure. Like, you're not going to get credit for that one. I mean, you won't. You'll hopefully have seen CO2 enough that you'll be like, that doesn't look right. Okay, so yeah, I guess we can try this real quick. I'm trying to think how much time we have. There it is. Thank you. Yeah. Okay, we've got time. So let's try this. If there's a nitrogen in there, nitrogen 1. What's the formal charge in that nitrogen? Molecules yet. Oh, okay, we'll get that. All right, I'll wait for a minute. It's hot in here. This room's always next door. The giant office is like freezing.
It's winter weather.
I was wearing this and a coat in there. That's how cold it is in there. Here, I just want to take everything off. It's so hot. All right. So everybody gave it a try. So the answer here is C. And you know, it's 5 valence electrons minus the 2 lone pair electrons. So 5 goes to 3, and then 3. There we go. And then 2, 4, 6 electrons. Half of that is 3. Those are gone. 0. Now, in the lab, hopefully you remembered that I gave you this shortcut for doing Lewis structures. Carbon has 4 bonds. no lone pairs. Nitrogen has 3 bonds, 1 lone pair. Oxygen, 2 bonds, 2 lone pairs. And the halogens, so fluorine, chlorine, bromine, iodine, in general, 1 bond, 3 lone pairs. What this is a shortcut for knowing whether you have a zero formal charge or not. So these are the most common ways you'll see the connections made in a molecule. Not always, but this is like a surefire way to do quickly, hey, double check to see if my structure's good. So notice the nitrogen, 3 bonds, 1 lone pair. 3 bonds, 1 lone pair. You get zero formal charge. If it's not that, then you would expect the formal charge. So this next nitrogen, 4 bonds. So that's not zero formal charge. So come on. What is the nitrogen labeled nitrogen 2?
Can you open the?
What's that?
Can you open the?
Oh, I'm sorry. Yeah, you're right. Yeah. There we go. Okay. So you can take a guess here, I'm sure. Oh, good. Everybody got it right. All right, +1. Yes. So notice that this nitrogen here, same pattern, 4 bonds. It's got a +1 formal charge. This oxygen's got 2 bonds, 2 lone pairs. That's the 0 one. These, what are they? Well, the overall charge is -1. These are -1s. Plus, minus, minus, add up to -1. So even this nitrate ion that I drew has a bunch of formal charges in it, but that's the only way you can draw it. Okay. There's more to resonance than just this. I'm not going to talk too much more about it, but this nitrate ion that I drew, why did I put the double bond on this particular oxygen? Not for any reason, it's just by chance. I could have put the double bond here or here instead. And those 2 other options create the 2 other resonance structures you can draw for nitrate. So why do we care about resonance structure? And let me go back to that. If I draw those other 2 resonance structures, there is no distinctions between them. There's like no difference. They all have the 3 formal charges. They all have the plus on the nitrogen and the minus on the oxygens. So they're like equivalent. They're all the same in terms of whether one's good or not. And so what does that mean for us? Well, we're going to get to it next week, but really what it means is that the true picture of this ion is some combination of the different resonance structures. So instead of being a single bond, double bond, a single double bond, it's going to be some fraction of a like 1 1/3 bond. So these electrons, see these electrons that make up the double bond? So there's 4 electrons here. So imagine just 2 of these electrons, the ones that make up the second bond. They're actually mobile. They're actually moving around the molecule. So we'll get to that. It's kind of interesting. All right. So before we go, we need to make sure we know how to do this. Skip that. There's another one. There's another one. So I'll show this one real quick, but here's just another molecule, slightly different construction to this one. So this has carbon in the center, that has nitrogen in the center. If you do the formal charges in these, I think it's pretty clear which is the correct one. Probably A, because it has the smallest formal charges. You might think maybe this one because it has fewer formal charges. And in reality, it actually might be a combination of these 2. Definitely not that one. That's way too big. But it gets a little muddy when we start mixing these. We'll come to this next week. Come back to it. Here's nitrous oxide. This is laughing gas. Yeah, question?
So, sorry, about the previous one.
Yep.
So is -3, like, is it just because it's like farthest away from 0, it doesn't matter
matter whether it's positive or negative. A large negative or a large positive they're both equally bad.
Okay.
Yeah. Okay, so very quickly, this is nitrous oxide. This is laughing gas at the dentist. This is also nitrous in car racing. When you attach this little tank to your car and you suddenly get a lot of horsepower. I can't explain the laughing gas, how it works, but I can explain the car stuff. So if you look at the formal charges, and I know the dots are all screwed up, but the bonds are fine. This is the one that looks like it's the best, right? Because we have 0, plus, and minus, and the minus is on the oxygen, whereas the 0, plus, and minus is on nitrogen here. This is better. Having a negative on the more electronegative atom is better. So if this is what nitrous oxide looks like, how does this work in a car engine? Why does this give you so much extra horsepower? Well, cars use fuel and oxygen. You need oxygen to burn the fuel. The more oxygen you have, the better it'll burn. So that O2, the double bond, in regular oxygen, takes quite a bit of energy to break. It's not as easy as you'd think. This bond is a lot weaker. That oxygen comes off so much more easily than the oxygen from this molecule. So once you dump this into your engine, it burns so well with all this extra free oxygen. That's where you get all the horsepower from. And it also blows up your engine if you're not careful. But
sorry.
Yeah, go ahead. Yeah.
I was gonna ask, like, phosphorus oxide. They've got the same valence electrons as nitrogen and phosphorus. Would that be of the same effect, if not more powerful?
So phosphorus is a little bit funkier because it doesn't make diatomic molecules like nitrogen does. It makes a little bit, so it's, the fact that it's bigger already makes it a little trickier to work with.
Yeah.
And I don't know if it would make a gas. So nitrous oxide is a gas. I think the heavier phosphorus would make it a solid, probably.
Okay.
Because I don't know exactly, but
Sure.
as far as working the same way as nitrous oxide, it's more complicated. I think the d orbitals make it complicated too.
Right.
So if you didn't know, elemental phosphorus exists as P4, not P2. It makes this weird thing that looks like this. Kind of like a pyramid of phosphorus. That's what it does. So phosphorus chemistry is a little bit tricky. Okay. All right. Here is we have 10 minutes for this. All right. Here is the goal now is, well, we have all these Lewis structures. Can we tell if they're polar now? So it's more complicated than just looking to see if it has a polar bonds in it. You have to also consider the shape. And here's why. If you so carbon dioxide has 2 polar bonds in it. Let me just remind you, looks like that. Alright, that CO bond is very polar. The other CO bond is very polar. But because it's linear, these dipole moments are canceling each other out. One points to the right, the other points directly to the left. So they're kind of fighting each other in terms of which side gets more electrons. Remember, the arrows point to the more partial negative charge in each bond. So in this bond, this is the partial negative side. In this bond, that's the partial negative side. So when I look at that molecule, can I say, oh, there is definitely one side of that molecule that is more negative? No, I can't. The dipole moments have canceled each other out. There's no one side that is more negative. And here's that electrostatic potential thing. Yeah, it's a little bit orangish on the edges, but it's on both sides. It's not greater on one side than the other. So this is a non-polar molecule, despite having polar bonds in it. And it's all because of the geometry. It's because of the shape of the molecule. Okay. Yeah.
It's centers of partial positive and negative charges lie at different places. Like the center of the partial positive and negative of that CO2 molecule do lie at different places on the molecule, don't they? But they just lie linearly separately, like they're symmetrical on each side.
So what do we mean centers of partial positive? So we're talking about when you consider all of the atoms together. So not looking at each bond separately, but looking at the combined picture. It's a very awkward way of saying that, honestly. But so so this is the combined picture, and there is no one center. Like, so when I look at, this is a slightly orange side, that's slightly orange. On average,
It's
it's
gonna be
right in the
there.
center.
So if there's more than one center, then it would be dipole.
Let me, maybe, if I show you the contrasting example, I might clear things up.
Okay.
And we'll come back to this. So water, so that's nonpolar. Water is the ultimate example of being polar with two polar bonds. Kind of the way CO2 has two polar bonds. But because water is bent, the shape causes it to be completely different. So,
Just a quick question.
Yeah.
Is the bent shape always going to be polar? Can
No.
that be a quick way to think
Not
about it?
always.
Oh.
I will give you an easy way to look at it in a few minutes. First, we're going to look at the visual way, which I understand not everybody can get. Some people are like mind blind about 3D things in their head, so I understand. But for water, this is water, and if I draw the individual dipole moments, right? Oxygen is more electronegative than hydrogen, so we'll draw an arrow going this way. And then for this bond, we'll draw an arrow going this way. So instead of looking like the CO2 where the arrows are either pointing directly away or directly at each other, these are both pointing upwards together. So the overall dipole moment is kind of in this direction, which is what that's showing up there.
So they don't cancel out, maybe.
Well, okay. If you have taken any kind of vector math course at all,
Yeah.
the way you would do this is you split these vectors into x and y components.
Right.
There's an x component and there's a y component.
Yeah.
The x components cancel out.
Right.
The y components do not.
Right.
They add.
Right.
So that's what I would say to you.
Okay.
Okay. But I think visually you can see it too. And if you can't, I will promise I will show you a shortcut that pretty much works. So that's polar. Ammonia works the same way. It is a polar molecule. It is trigonal pyramidal. So after you do the Lewis structure, you find the shape. It's trigonal pyramidal, and because it's in this pyramid shape, all these dipole moments that point towards the nitrogen add up to something that kind of points overall that way. So that's a polar molecule too.
So if the dipole moment is pointing in the same direction, we can assume that the atom is polar?
The molecule is polar.
The molecule.
Yes.
The molecule.
Yeah. Mm-hmm. So dichloromethane is a good example. So this slide is showing you the easy way to look at it. But if I were to show you on a test, I would say, and I would draw it like this. I would say, is this polar? And if you were not careful, you would think, oh, that's a polar bond, and that's a polar bond, but they're pointing in opposite directions. Oh, it's nonpolar. That's not the shape, though. This is how we draw it on the board. This has a tetrahedral shape. So, first I'm going to say that's not correct. I mean, it's the Lewis structure, but it's not how you do the dipole moment. This is tetrahedral. So, how does it really look? tetrahedral does this. And where you put the CLs and where you put the H's doesn't matter. But that's what tetrahedral looks like. So I think here it's a lot clearer. You have a dipole moment that way and a dipole moment that way. It's pretty much pointing in that direction overall. That is a polar molecule. So it's not nonpolar, it's polar. And you have to know the shape in order to figure out the polarity. Okay? Here's formaldehyde. That's polar. So again, we kind of ignore the CHs, right? Because even though there's a small difference in electronegativity, I'm telling you that we consider them to be nonpolar. So just pretend it doesn't have any dipole moment there. But there is one here. Okay. Yeah.
Hypothetically, if we were to switch one of the hydrogens and one of the chlorines, like the top hydrogen with one of the chlorines,
Yeah.
that molecular geometry technically wouldn't be wrong, right?
No, it's still the
But
same.
what
Yeah,
if-
it'll be a little harder to see the dipole moment, but it's not going that way, so it's going that. You have to really think 3D in this case.
Okay.
And like I said, if this is difficult, which is difficult, I have a better way to show you, and I'll do it right now. Yeah. So real quick, BF3, I showed you that. This is nonpolar. Notice that even though every one of these bonds is polar, they kind of all point in symmetrical directions, so they all cancel each other out. Nonpolar. And here's an example of a tetrahedral molecule. It's all symmetrical. The fluorines all around, they cancel each other out. It's nonpolar. But as soon as I replace one of those fluorines with a hydrogen, suddenly there's an imbalance. It's not symmetrical anymore, and it's polar again. So this is the clues to how I'm going to show you. So the rules are, let me just write them down so that you have them. Think of it like a computer program. You can find if something, well, let me start off by saying, if the, number one, and both of these have to be true, if the electron geometry is the same as the molecular geometry, all right, and the outer atoms are all same electronegativity. So that means they can be the same atoms, they'll be the same electronegativity, or they'll just be different atoms, but still same electronegativity, like carbon and iodine, they're the same. If those two are true, and both of them have to be true, then it is nonpolar. If one of these is not true, or both is not true, then it's polar. That's the shortcut. So if you can't view this three-dimensionally, then you can kind of go through these two steps. So how does this work? Well, I'm going to go through geometries quickly, so I know that some of you are not good with it yet. This is both tetrahedral electron geometry and tetrahedral molecular geometry. So condition 1, good. All the outer atoms are the same electronegativity. Condition 2, good. It's nonpolar. Same geometries, but they're not all the same on the outside, so it's suddenly polar again. If I go back, BF3, trigonal planar, trigonal planar. All of them the same on the outside, nonpolar. Going back to here, so formaldehyde. This is trigonal planar. Trigonal planar electron geometry, trigonal planar molecular geometry, but then all of the atoms on the outside are not the same electronegativity. So that's no good. It's not. It's polar now. What's another one? Water. I mean, here's the example. Water is tetrahedral electron geometry, but it's bent molecular geometry, so that's no good. It's polar. So I think these rules are fairly universal. I haven't really found any examples that don't work. So this is a good way to quickly find if something is nonpolar, and if it is not nonpolar, then it's the other one's polar. Okay? But again, there's a lot of steps that go into this. You have to do Lewis structure first, then you have to find the geometries. And only then can you determine whether it's polar or nonpolar. So molecular polarity is a lot. Good quiz questions for next week, right?
So we're a quiz on Thursday next week? Or Tuesday?
Yeah, let's do one.
On Thursday.
On Thursday, yeah.
Oh, sure, why not?
I mean, yeah, it's a good study, right?
Yeah.
You can boost up your quiz grade, and the worst that can happen is you'll have an average score that doesn't move your quiz grade, right? Or I guess the worst can happen, it'll be worse, but I don't think that's 0. So I think everybody got their exams back, or if you didn't get yours back, let me know.
I had a quick question. Is the final accumulative or just on this last
Oh,
section?
yeah, good question. The final is kind of cumulative. So I will, for instance, ask questions specifically about significant figures. Because there's not a lot of new stuff. There's going to be 2 weeks worth of new stuff. So maybe a third of it will be brand new stuff, and then the rest of it will be old stuff. So it is going to be cumulative. It's kind of how finals are.
From the very first exam?
Yes. So I would use, all the previous exams, quizzes, and labs, studies. Yeah. And I haven't heard that part, but.
I'm sorry?
I'm evaluating my first, definitely first semester.
Oh,
My long-term memory's not that great.
What is the
Oh, Max.
atomic mass of
You're right.
iron or something? You know.
Never mind.
Or like isotopes and isomers.
Alright, hold on the rest and give it to you next week, but.
I know the process, but I wanna understand that way.
The
Sorry,
visual
what?
part of it.
Question.
The best thing I can think of is, so the lab next week will help a little bit. I don't know how comfortable you are with the shapes yet. So like using that simulation website just to like build a molecule.
That's in the lecture. Do we just look up?
If you want to email me, remind me, I can try. Let me see if I can post it right now. And it's easily searchable. PhET, molecular shapes. Yeah, there it is. Let me see if I can just put it on the front page real quick. Oh, it's so slow. Come on. Okay. There's a link there. Hopefully it works, but that's the link on the activity feed on the main front page that leads to that website.
Okay, so,
Yeah.
I might be traveling on the day of the exam.
Okay.
So if I am gonna travel, can I do it on Monday, the day before?
Yeah, I have a class on Monday that's doing the same final. It's 12:30, same time as our class. If you want to show up on Monday, that's fine too.
Okay, I'll just let you know if I am going.
Yeah, that'd be nice, so I can print out extras, yeah.
Okay.
Yep.
Thank you.
I should offer this to anybody, honestly, because if you guys want to take it early, I'm fine with it. But I think hope some wants to study time, so.
I might have time to get to the MyLab mastering this weekend.
Okay.
Anytime soon, actually,
Okay, well.
I don't know what you want me to do, but I gotta catch up. I missed a week of biology.
I understand everything.
Yeah.
So, if the plan, so your plan is to finish on time, so let's just say by the final. You can hand in to me stuff by the final. That's good enough for me right now, okay? Alright. Yeah, let's see. I think I found all the people who were like in real danger, but so you're worried about the lab grading, really, right? I mean, you seem to be okay in the lab grade. I haven't graded the last lab, I haven't turned it in or not, but you know, your lab's fine. Probably consider it a midterm grade. Let's see overall. Yeah, so you're right on the border of like, so let's see. So you're right on the border. I can't tell you what you might think you want to do. Are you going to continue and do 222, or is this your only class?
I think this is the only one.
So I would have said if you were going to do 222,
Mm-hmm.
you might not be as comfortable with the material as you would want to be for 222.
Mm-hmm.
But if you just need to pass, and you don't care about the grade, I think you could still pass. I don't know. It's up to you. And I wouldn't worry about next term if you're not going to take 222.
Okay.
So it's up to you. It's whatever you think you need to do. I mean, maybe withdraw now you have a W. If you were looking for a better grade for like, I don't know what you're going to do next, applying to summer school. It's up to you what you think looks better.
Yeah.
So.
Well, I'm actually gonna have time to study, so
Okay.
I think I can do good.
I mean, I think you've been doing okay. So I think was there homework or maybe you were doing plenty of homework. So yeah. Oh, I think you got behind with a little homework. I have to just grade some of that. I haven't graded yet, so maybe that's what it is. Yeah, I think you have a good shot of passing the class line. So there's only this is the new stuff, and there's gonna be a little bit next week, but it's a minor part. So you have your old exam, you know what you did wrong, hopefully you can bring that up. And if you want, we can go over some stuff on office hour days. So I'm here Monday mornings and Thursday mornings, pretty much all morning. I have a tiny bit of time after class, but you know, not as much. So it's up to you if you want to go over some stuff in one-on-one. Just let me know, okay?
Okay. Yeah, thank you.
Okay.
realized I did so many stupid mistakes, like just mixing up the opposite even more than that.
Mm-hmm.